Okay, I thank the organizers for this opportunity. I'm very glad to be here. During the last 15 years, my team at Ia SNe has been measuring the ages of stellar populations in type 1a supernova host galaxies. So today I'd like to share with you some interesting discoveries from our investigations. Okay, this is just to remind you that what they found in supernova cosmology is that the supernovae at high redshift are fainter by about 0.25 magnitude compared to the model without dark energy in this Hubble residual diagram. And this is interpreted as evidence for an accelerating universe. But as Beatrice Tinsley pointed out a long time ago, there is a possibility of luminosity evolution in the standard candle, since stellar populations in host galaxies become younger with increasing redshift. It is therefore possible that the high-redshift supernovae are fainter, partially because their progenitors are younger compared to local counterparts. Indeed, during the last 15 years, host galaxy studies found correlations of supernova luminosity with host galaxy properties such as host mass. So now the host mass step correction is routinely applied in the supernova distance key. However, mass over host galaxy cannot tell a supernova in it to be bright or faint. So many people, including my team, suggested that the root cause of the mass step must be something else closely related to host mass, such as progenitor age. In order to check the effect of age on supernova luminosity, of course, we need to directly measure ages of stellar populations in host galaxies. But to my surprise, such a direct and reliable age measurement in host galaxies has been lacking in the literature for some long time. So 15 years ago, we decided to measure reliable population ages of host galaxies by obtaining very high quality spectra of nearby early type host galaxies. And our project has since been extended to host galaxies of all morphological types by employing the photometric age measurement of Conway and Gunn. So after some 9 years of hard work, we first found a very important hint of 3 sigma correlation between host age and supernova magnitude from spectroscopic age measurement of early type host galaxies. And then from the Rose-Edel sample and their photometric age measurement, we found a 4.3 sigma correlation between host age and supernova magnitude for host galaxies comprising all morphological types. And this result has been independently confirmed by 2 third-party confirmation, UC Berkeley team and Chinese team at more than 5 sigma. And now, recently, we remeasured ages for a larger sample of host galaxies in a broader redshift range, including the Rose-Edel sample at relatively low redshift and the Gupta-Edel sample at relatively high redshift. And we confirm the universal nature of this age bias at 5.5 sigma for the Rose-Edel sample and 4.3 sigma even for the Gupta-Edel sample at higher redshift. You know, 5.5 sigma correlation is very rarely obtained in astronomy. Therefore, this correlation should not be ignored. If we ignore, we'll end up with an incorrect cosmology or some tensions in cosmology. So I was wondering, what would be the origin of this strong correlation between population age and supernova magnitude? It turned out that unlike the key assumption of supernova cosmology, there is a strong progenitor age dependence in the supernova luminosity standardization process itself. The Phillips relation, light curve width luminosity relation, Kala luminosity relation, two correction terms in the supernova luminosity standardization process. And as we see here from the Rosetta sample, supernovae from younger progenitors in red, in blue are fainter compared to those from older progenitors in red, each at given light curve shape parameter x1 or at color parameter c. Therefore, after the luminosity standardization, which is nothing but the rotation of these diagrams based on the slopes, alpha and beta. So this is before the luminosity standardization, and this is after. Before, after. So after the standardization, supernovae from young progenitors in blue are overcorrected and become relatively fainter. Want to see more? Before, after. The problem is, high redshift supernovae are also from younger population. Therefore, they should be equally overcorrected and become similarly fainter. And this is a 4.6 sigma result, but other host properties, such as host mass, metallicity, and dust content, they show only insignificant offsets in the same diagrams, indicating that progenitor age is the root cause of the correlation, reported correlation between host property and supernova luminosity. A similar result is also obtained from the group-tidal sample at relatively high redshift, before the standardization and after the standardization. After the standardization, younger progenitors are overcorrected. And the history of H0 determination is telling us that we should be seriously concerned on this luminosity offset, because this is reminiscent of Bade's discovery of two separate period luminosity relations varying with population age. Very familiar story. And as such, our finding must cause a serious systematic bias with the redshift in supernova cosmology. From the well-known cosmic star formation history, we can actually calculate a supernova progenitor age distribution as a function of redshift by convolving the delay time distribution of type 1a supernova with cosmic star formation history. Here we can see how the population ages and supernova progenitor ages in host galaxies are getting younger with redshift, which are well supported by these observational data. In relative sense, both population age and progenitor age, they evolve very similarly with redshift. And within the redshift range most relevant to supernova cosmology, we expect a 5.3 gigayear variation for the progenitor age, and therefore 0.16 Mach evolution in supernova luminosity only because of the age bias, which has nothing to do with cosmology. This indicates that in this Hubble residual diagram, the observed dimming of high redshift supernovae relative to the model without dark energy is partially attributable to the redshift evolution of progenitor age. Therefore, accordingly, a correction is required to remove this age effect to see only the cosmological signal from the supernova data. And we made that relative correction as a function of redshift to the supernova data. This is before the correction, well supporting LCDM model. But after the correction for the progenitor age bias, the supernova data set no longer support LCDM model, but very interestingly, is more consistent with a time-varying dark energy model as recently suggested by DESI BAO and CMB, with the value of W0 of minus 0.42. In the same W0 LCDM model favored by BAO plus CMB, here we compare supernova distances in blue with BAO distances in magenta from DESI and yellow from DES. It is very clear from here that before the correction for the age bias, supernova distances do not match with the BAO distances. But after the correction for the age bias, supernova distance scale matches very well with the BAO distances all the way up to redshift 2.5. Therefore, our revised standard candle is in excellent agreement with the standard ruler in the W0 WACDM model favored by DESI BAO and CMB. For more detailed cosmological analysis, following this DESI BAO paper, we have also combined a supernova data set with DESI BAO and CMB, and then compared that with the probability distribution predicted only by DESI BAO and CMB. And this is the result. Before the correction for the age bias, supernova added result, they still lie close to the LCDM model. They are not placed at the center of the distribution predicted by BAO and CMB, but they lie at the outer skirt of the distribution, indicating some discordance with DESI BAO. However, after the correction for the age bias, supernova added result aligns more closely with DESI BAO and CMB. W0 moves from here to here, aligns better with BAO plus CMB in gray. WA moves from here to here, again aligns better with BAO plus CMB. And the deceleration parameter Q0 also agrees better with CMB, with BAO plus CMB after the age bias correction. Therefore, now we have a new concordance in cosmology when our supernova distance scale is corrected for the progenitor age bias. With a 9 sigma discordance with LCDM model, strongly suggesting time-varying dark energy equation of state. One of the important and interesting implications of our result is the deceleration parameter Q0. When the DESI BAO result is combined with the CMB and supernova before our age bias correction, the future universe will transition to a state of decelerated expansion, as recently suggested by DESI BAO papers. However, even in this case, the present universe is still in the phase of accelerated expansion with negative Q0. However, when the supernova data set is corrected for the age bias, the red curve shows here that the present universe is already in the phase of decelerated expansion. This is not something peculiar because this is fully consistent with the prediction obtained when the DESI BAO is combined with the CMB in blue curve. Therefore, DESI BAO is strongly supporting our result. Only that was not highlighted in the DESI BAO paper because they were combining supernova data without knowing our age bias correction. For more direct cosmological test, without worrying about the progenitor age bias and overcorrection in the luminosity standardization, we are also performing evolution-free cosmological test where we use only supernovae from young and the same age host galaxies across the entire redshift range. And from the cosmic star formation history, and also from the direct age dating of high-age galaxies, we know that the mean age of host galaxies at redshift 0.7 is 3.1 gigayear. Therefore, we select only equally young host galaxies from the Rosetta sample and from the Gupta sample, so that their mean ages also become 3.1 gigayear. So the binned data here in green, they all have the same age across the redshift. But as we see here, they still prefer the same W0 LCDM model favored by BAO plus CMB rather than LCDM. Of course, we need to fill the gap here and there, but we can already see the conclusion from this preliminary analysis. So before I conclude, let me remind you that the same, the two tests that I presented today has also been highlighted by Lee et al. And other people in their discovery papers. So we are not inventing anything new. We are simply following their suggestions, but more directly with measured ages rather than using proxies. And we are getting different results. So let me conclude. There is a 5.5 sigma evidence for strong progenitor age bias in supernova distance scale. And when the three different samples are combined, we have a 7 sigma result. And when that system bias is corrected, then our revised standard candle is in concordance with the standard ruler in the W0 WCDM model favored by DESI BAO plus CMB. And when three cosmological probes are combined, when BAO and CMB are combined with our revised supernova scale, we strongly suggest two things. Number one, dark energy is no longer in the form of a cosmological constant. And number two, the present universe is no longer in the state of accelerated expansion. Overcorrections in the luminosity standardization process was mimicking presently accelerating universe with cosmological constant. And finally, the same effect could also help alleviate Hubble tension, and so work is in progress for that. So thank you, I stop here.
Thank you very much for your talk. So, yeah, let's start.
Just to make things clear, what exactly do you mean by progenitor? Do you mean the galaxy in which the explosion happens, or the white dwarf in the binary system, or the partner in the binary system?
Usually, for host galaxy study community, we measure the average age of stellar population in host galaxies. And sometimes we measure the local area around the supernova. So if we have only one supernova at each redshift bin, then this can be a problem because there is a possibility of local to global difference. But we have many supernovae at given redshift. So on average, they should follow the same expected luminosity evolution curve and the age evolution as a function of redshift. We are not alone. All the supernova host galaxy community is measuring the global property either or the local property near the supernova site within a host galaxy. And they generally do not show any big difference.
Okay, any other question?
Thanks for your talk. You know, most of the time, us supernova guys get a hard time for showing any evolving dark energy signal. And you're saying our evolving dark energy signal is not nearly big enough, so it's nice to balance that out. My question is, have you looked at any of the bigger samples, like ZTF or DES or Pan-STARRS? Because when we look at them, we see very strong color dependence with any of these effects, which would imply not progenitor, but something dust related.
With the supernova sample that I showed was DS sample, only the binned data. But the Pantheon, they show the same result because we are comparing both the DS and the Pantheon.
No, I mean looking for any kind of step effect.
Yeah, this was a DS, but the Pantheon, we have more or less the same result. But the Pantheon had a strong, very ad hoc mass step correction, so we were not able to use that for the progenitor age bias correction because there should be no additional corrections, more than the alpha and beta.
Okay.
Over there.
Hi, thanks very much. I'm curious about the final posteriors that you have before and after correction. Can you show the plot with the posteriors in dark energy?
You mean this one?
Yeah, just there, great. I'm curious about how much the constraining power changes when you make your correction, because your correction must have some uncertainty on it and that folds through into the final posterior. So how much does how much do the contours blow up because of the choice, because of the correction that you make?
I'm having some hearing problems.
Okay, then we can discuss over coffee. That's fine.
Okay, but yeah, this is happening. If I'm getting correctly your opinion, we are getting this difference was already expected in this diagram. And I mean, oops, no. I mean, in this diagram, that result was already expected.
Any other question or comment?